We're going to complete a couple of applications of our trig derivatives. So the first one is actually asking you to determine the absolute extreme values for this particular function between a fixed interval here. All right, so for those extreme values, we're really just talking about maxes and mins, but we do have a fixed interval, so we have to work with that. Now, this function has two pieces here, and they're just being added together. So I can just do the derivative of the first one separately from the derivative of the second. It's not like a product rule where I have to worry about multiplying anything. So the derivative of cos x is negative sine x, and our derivative of sine x is just cos x. So there's our derivative function. And we need to set that derivative equal to 0 to find our possible critical numbers here. So we would end up with 0 equaling, I'm just going to flip that around and put positive cos x first and then minus sine x. We want that to equal 0. In other words, we want to know what values of x make sine x equal to cos x. I'm just adding sine x to both sides. So what values of x make sine x and cos x equal to each other? So we have to think about that for a little bit because we don't have an easy way to go ahead and solve that. But let's think about our trig relationships here. So sine looks like that over 0 to 2 pi, and our cos looks like, now I got to try and line these things up, minimum, back to 0, back to maximum. Okay, so these two graphs are actually intersecting here and here. So that's where those two graphs are equal. Now the question is, where are those actually happening? So we know that pi over 2 would be right here, and this spot, my diagram is not super awesome, but this spot here is, this spot here is pi over 2, and this spot here is pi. I think I mixed it up when I was saying that out there. This spot is 3 pi over 2, and then we're back to 2 pi right here. Okay, so we have the zeros of our, zeros of cos and the zeros basically of our sine curve. Now, that means the first intersection point is happening prior to pi over 2. I want you to think of our special triangles here. Where would, if I draw my special triangle, if I draw a triangle, where would we have the sine x and the cos x being equal to each other? Well, sine x is just opposite over hypotenuse. Sine x is opposite. Oh dear, didn't do a good job of that. Let me try again. Oops, that was supposed to be the eraser. There we go. All right. Live, not quite live, but I could re-record. I'm not going to though, because boy, oh boy, these take a long time to do. All right, opposite over hypotenuse. So that really is our y over our radius if we talk about that unit circle. So that would be equal to cos x, and remember cos x is adjacent over hypotenuse. Adjacent over hypotenuse. These would be equal to each other where adjacent and opposite are equivalent to each other. In other words, where x equals y, which means this is an isosceles triangle for this to work. So if it's isosceles, I can think of that as, like, if this was 1 unit long, this would also be 1 unit, and that's a special triangle of 1, 1 square root 2, which is our 45-degree angle, or our pi over 4. So these are going to be equivalent when x equals pi over 4, and also they're equivalent here, which is somewhere between pi and 3 pi over 2, which throws us down into this quadrant if we think of angles in standard position. And once again, we're working with our x equaling our y, which means our x is -1 and our y is -1. So that gives us our pi plus another pi over 4. So that's 5 pi over 4 as our other option. So x equals 5 pi over 4 is our other possibility there. Now I'll just run through that again in case you didn't quite catch that. We know that this angle here, the red that I've just identified, that is pi. And then the special angle in here would be a pi over 4. So altogether, that angle in standard position would be pi plus pi over 4. And pi is really 4 pi over 4, which adds together to make 5 pi's out of 4 5 pi out of 4. So that's where I've come up with my two possible critical numbers here. Now, we have a closed interval, so all we need to do at this point is actually evaluate f at the endpoints of the interval and at our critical numbers, and whatever works out to be the biggest is our max, and whatever works out to be our smallest will be our mins, if possible. Now, f at 0, cos of 0 is 1, and the sine of 0 is 0, so f at 0 is 1. Similarly, at 2 pi, we're one full cycle beyond, so it's also going to be 1 plus 0, which is 1. So we have our possible values of 1 here. Now let's evaluate f at pi over 4. We know that the cos of pi over 4 would be 1 over root 2. And the sine of pi over 4 is also 1 over root 2. So that makes 2 over root 2. 2 over the square root of 2. Now sometimes people were letting me know that their answers weren't matching Bob's answers. It could be sometimes they are rationalizing our denominators here. That's going to give us 2 root 2, and then root 2 times root 2 on the bottom gives us the square root of 4, which is a 2. And then the 2's reduce, and that leaves us with square root of 2 here. I'm also going to do f at 5 pi over 4. So f at 5 pi over 4, that cosine would be negative 1 over root 2, and our sine would be negative 1 over root 2. So that's going to be negative 2 over root 2, which also I could do the rationalizing of the denominator, and that gives us a negative root 2. So we have, if we take the decimal amount to these, square root of 2 is about 1.414. So that's bigger than 1. So this is our absolute max, and then this one would equal negative 1.414. So that would be our absolute min on that interval. So you just want to make sure that you conclude that with a final statement there. All right, the next question is a tricky question. It's one that pops up now and again, but it's a tricky question. It's a triggy question. It's one that involves trig here. A shed is built up against the side of a house, and the side view is shown. What is the shortest ladder required to touch the house that also touches the top, top of the shed? So I've tried to draw the side view diagram here, and label some things for you so that you understand what I'm meaning, hopefully. So we have the shed, and I've given you the dimension of the shed. The shed, the shed is the shed is 2.5 meters high, and the house continues up farther. In fact, that wouldn't be the roof of the house. The house would continue up, and we're gonna put this as our ladder right here on the angle, going from the ground up to the spot up here in the house. And then the shed is only 1 meter wide here, and of course I've labeled the ground. So this is across a side section of what we have here. All right, so we need to figure out the shortest ladder that's going to touch the house but also touch the top of the shed. So it's just trying to brush, I did my best to draw that there, that it's just touching the top of the shed, the top corner there. So we've got to figure this out in terms of how we can work this out. So we're going to come up with our equation here. Now I want you to let theta be the angle that the ladder is making with the ground. I'm going to let theta be that. And because we've got the ground being parallel to the top of the shed, it means that this angle up here in the small triangle up in the top is also theta. And I'm going to break this down into pieces of the ladder. I've got this ladder, the part of the ladder from the ground to the top of the shed, I'm going to call L1. And then from the top of the shed to the house, I'm going to call that L2. And what I want is to have the shortest ladder. My ladder in total would be L1 plus L2, and that's the thing I want to minimize. I want to get the smallest of. So let me put some therefore statements, or some let statements down here, and then we'll go from there. Okay, so I have some information written down in terms of let statements. I couldn't find a theta on my iPad, so I just put in the word theta. One other thing before I get into this ladder length is I need an expression to actually represent those L1 and L2 values. I know that I have a right angle triangle down here at the bottom with the shed and the L1. And I know that shed length is the 2.5 meters. So my sine of theta is going to equal 2.5 over L1, which is the hypotenuse. So I'm just going to write that down up here so that I have that sine of theta is going to equal the 2.5, the height of the shed, divided by the hypotenuse. So just in case you're not sure what I'm using here, I'm using this green right angle triangle right there. Okay, so that comes from there. Then if I look at this nice little triangle up here at the top, which I'm outlining in red, I need some information for that. Well, I know this time, I know the bottom length is 1 meter, so that's the adjacent to my theta. So I could say that the cos of theta is going to equal 1 over L2. Okay, so let's use those in our equation here. We want our ladder length to be minimized, and my ladder length is just L1 plus L2. If I rearrange my equation that I've underlined in green here, I know that L1 is just going to be equal to 2.5 divided by the sine of theta. I've just rearranged that, and if you're not sure about that, I will actually rearrange this one. I would rearrange, I'm going to multiply both sides by L2, and then divide both sides by cos of theta. L2 will equal 1 divided by the cos of theta. Okay, so we have plus 1 divided by the cos of theta. At this point, we are ready to take our derivative of the function. So I'm going to start over here just to give myself some room, and hopefully I can make this fit. So our L prime at theta is an independent variable here. I'm going to look at this as two separate pieces. So the 2.5 over sine theta, I'm going to treat that with the quotient rule. The derivative of the top would be 0 times the bottom, sine theta, minus the derivative of the bottom, which will be cos theta, times the top, all over the bottom squared. And then we're going to take the derivative of 1 over cos theta. So the derivative of the top times the bottom, minus the derivative of the bottom times the top, times 1, all over the bottom squared. Okay, so the derivative of cos theta and sine theta, you just need to know them. We use them so much, the practice should get you there, and you just know what they are. 0 times sine theta will just be 0. So on the top, we're left with minus 2.5 times the cos of theta. So I'm just tidying this up all over sine squared theta. And then we're going to have 0 times cos theta, which is 0. And then take away a negative becomes a plus. And then we have sine theta over cos squared theta. Now, to be able to work with this, I want to find my critical numbers. And to get the critical numbers, I'm going to let the derivative equal 0. And from there, we are going to, we have a couple options. We could combine this as a single function, or I could add 2.5 cos theta over sine squared theta to both sides of the equation. And I think that's what I will do with this. So 2.5 cos theta over sine squared theta will equal sine theta over cos squared theta. All right, so I have a proportion here. I have one fraction equal to another. I could multiply both sides by cos squared theta and multiply both sides by sine squared theta, and I just realized I forgot my theta there, and that will, so it's like cross multiplying here, that will get things from the denominator here, and let's see where we can go from there. Now, I'm almost out of time on this video, so I'm going to start at the next video at this point.